Okay, folks, I want to go over two optimization problems that seem very similar. This was from your optimization notes, section 4.5, and we'll look at questions number 16 as well as number 17. So read through them, pause the video, read through both these questions, and take a moment to think about how these two questions are similar and how they're different. So I'm going to go ahead and get started on number 16 here. And in this case, the directions say we are confined by the amount of material we have. We've got 2,400 square centimeter material to make a box. This box must have a square base and an open top. Those are the requirements for it, and as well as the fact that we can only use the 2,400 feet of fencing or material. And our goal is to come up with the largest possible volume for the box. Okay. So this is a classic optimization question, and so what do? Well, typically what we do is we come up with two different functions. The first one is the optimization function. Sometimes it's also called the objective function. And it is the function that you're being asked to optimize. Well, in this case, we're not asked to find the material for the box. In fact, we know what the material for the box is. Instead, we're asked to find the largest possible volume for the box. So we want to optimize the volume of this box, and here I'll go ahead and put x, y, h is equal to x times y times h, and let me explain my choice here in just a second. So if we had any old box, this box would look something, I don't know, I'm not so great at 3D drawing, but this box would look something like this. Okay, so we'd have this dimension here x, we'd have this dimension here y, and we'd have this dimension here h. And how do you find the volume of a rectangular prism like this? Well, you simply take the product of the length, the width, and the height. But I actually want to jump back to our question because it didn't say that this could just be any old box. In fact, we were given the parameters that it must have a square base. So if we think about this box sitting on the surface here, this dimension and this dimension must be the same. So although this picture is true for any old box, what we're actually after is a box with a square base. So let's go ahead and draw that correctly. So instead, we want our box to look something like this, where this dimension here, if this is x, this will also be x, and then the height of this box will be h. So in fact, let's return to our objective function, and we've already got one of the three variables eliminated. We have x squared times h. That gives the volume of the box. So now I can think of it as just a function of x and h. So folks, if I did that too quickly, pause the video and just take a moment to think about this. We're told we have to have a box with a square base. So that means that these two dimensions, if I call this dimension x and this dimension x, they must both be x. Okay? And then the height is free to be whatever it needs to be, provided we meet the constraint. So there would be the height. So this is the dimensions here, and how do you find the volume of a cube or any sort of rectangular prism? You do the length times the width times the height. So that's how I end up with our objective function there. Let's go ahead and erase that. Okay. So what I've been telling folks is that, well, what I'd like to do is optimize this function. I would like to find the global extrema on this function. But this is a function of two variables, and we're not learning multivariate calculus right now. So our goal, and indeed the only way we can solve this problem, is to try to get rid of one of these variables so then we can actually take the derivative of this function. To do that, we're going to look at the constraint. And let me give you sort of a justification for why we have a constraint on this problem. We're being asked to find a box that's got a square base and open top that has the largest possible volume. Well, why don't I just make a box that's, I don't know, 5 kilometers by 5 kilometers by 5 kilometers? That would be a gigantic box. It would have a huge volume. Why can't I let that be the answer? Well, the reason why that won't work as a solution is that we are confined, we have a constraint that we can only use 2,400 square centimeters in constructing this box. So the amount of material we use, must equal 2,400 square centimeters. By the way, it actually doesn't have to equal 2,400 square centimeters, just that's the most we can use. But of course, if we're going to be efficient, we want to use up all the material we have. So now we need to come up with a function that relates the material used in this box. So we'll call it m of xh. Okay? And so this is how I want you to think about this. Let's suppose you were going to cut out each of the sides for this box. What would be the area of each side? So if we look at this first face right here, what is the area of this side? Well, it's got a length of x and a height of h. So the first side is going to have an area of x times h. Okay. Well, so would this side over here, right? This side right here would also have an area of xh, and we can't really see it from my drawing, but we have the back two sides of the four sides, the four vertical sides of this box. They all have an area of xh, and I've got 4 of them. So the amount of material spent making the sides of the box is 4 times x times h. But we also have the base of the box. Okay, so it's hard to see here. Let me see. I'll kind of ghost it in like this. Okay, so we've got the bottom of this box here. What's the area of the bottom of the box? X squared. Now you might be tempted to write 2x squared, arguing that this cube has a top, or this prism has a top and a bottom, but we were told actually this is an open top box, and so it'll just be x squared. Okay, so this is the amount of material. This is a function that would give the amount of material, but we're told that that is fixed to be 2,400 centimeters squared. Okay. So at this point, and this is sort of the way all of these problems go, we drew a picture to help guide our intuition, but then we came up with the objective function and we came up with a constraint function. Okay? So you should do that in nearly every one of these problems. Sometimes the constraints are built in, but otherwise you should always be coming up with both an objective function and a constraint. So what do we do next? Well, our goal next is to, again, return to the objective function, and we want to take the derivative of it, but I can't because I've got 2 variables in here. I've got both x and h, and I can't take the derivative of a multivariate function. So what could we do? Well, let's go ahead and solve this constraint for one of the 2 variables. In some of these problems, it matters which variable you choose to solve for, because that variable will be eliminated in the objective function. But in other problems, it doesn't really matter. Here, we're just asked to find the largest possible volume for the box. There's nothing that says which of these 2 variables we need to optimize. So let's solve for whichever one in the constraint is easiest to solve for. Well, notice that if I tried to solve for x, I've got that this is quadratic in terms of x, and it would be pretty messy. So let's instead solve for the variable h, because this function is linear in terms of h. So let's see here. If I want to solve this for h, we're going to first subtract over this x squared term, and then we'll divide both sides by 4x. So there's our constraint. Okay, well, why did I do that? Well, the reason why I solved the constraint for the variable h is now I can return to my objective function, and I can go ahead and rewrite it now not as a function of both x and h, but as a function of just x. So this gives me x squared, and then in place of this h in the objective function, I'm going to replace it with what we found h to be. We're going to substitute in an expression for x. So we get 2,400 minus x squared all over 4x. If I clean this up, let's see here, I'll distribute this x squared through to both terms, and then I'll divide both terms by 4x. So if I do so, I get 600 x minus 1/4 x cubed. So pause the video, simplify this however you wish, and see that you get down to this expression here. Okay, so that's our objective function. Okay, that's our volume as a function of x. So now let's go ahead and optimize it. So by that I mean let's find the global extrema on this function, or at least the global extrema that we want. So we take the derivative of this function, and we get 600. We've gone ahead and taking the derivative of this, we get v prime of x is equal to 600 minus 3/4 x squared. So now we want to find the critical numbers of this. Well, there's no place where this function is undefined, so to do so we only have to worry about setting the first derivative equal to 0. So that happens when 600 minus 3/4 x squared equals 0, or when 600 equals 3/4 x squared, or if we divide both sides by 3/4, we get 800 equals x squared. So that happens when x is equal to plus or minus the square root of 800. Now, depending on how you choose to define your function v, you either may or may not include that negative root. But it doesn't really matter, because on the interval from 0 to infinity, on the positive interval, x equals the positive square root of 800 is the only critical number. So sort of regardless of how you define the function, this domain, this is true. Okay, so now we've got this critical number on the domain that we're interested in, and we need to classify it as either a local min or a local max. So what do we want to do? Well, we want to take the second derivative of this function, and the second derivative of this function gives us negative 3/2 x, taking that second derivative, and then we're going to go ahead and plug in our critical point into the second derivative. Why am I doing this? Why am I plugging the critical number into the second derivative? Well, I'm checking for the sign on the second derivative. In this case, this has a negative sign. The second derivative is negative at that point, so v is concave down at x equals the square root of 800. So folks, I'm in the process here of using my second derivative test, and by finding the fact that the square root of 800 is a critical number of the first derivative, that is where the first derivative was 0, we know that we have a horizontal tangent line there. And by finding that the function is concave down at that point, if I put those two facts together, this is the fact that f is concave down near the square root of 800. But then additionally, we said that we have a horizontal tangent line at the square root of 800. So if we put those two ideas together, then we know that x equals the square root of 800 is a local max. Okay. But because this is the only local extrema on the interval 0-800, then by a theorem that we presented in our section, in the notes for this section, we have that x equals the square root of 800 is also a global max. This was, I believe this is we're in section 4.5, so this is section 4.5 theorem. Okay, that says if we have only one critical number, or let me say it like this, if we have only one local extrema on an interval, then that local extrema is also its corresponding global extrema. Okay. Well, now we need to actually, let's go ahead and give a decimal approximation for this. Let's see, this actually simplifies to be 2 square root of 20. I could simplify that further. Let's see, that simplifies to be 20 square root of 2, 20 square root of 2, which is approximately, just to give a sense of what x is, it's approximately 28.3 centimeters. Okay, but we're actually asked to find the volume, the largest volume possible. So now what do? We're not asked for both dimensions, although we could find not only x, which we found, but we could find the height. But we're asked to find the volume, so I'm just going to take the volume function and plug in the square root of 800 into it. And let's see what we get. So let's take this and plug it into our volume function. Well, the volume function was 600x, so in place of x we put the square root of 800 minus 1/4 times x squared, so that's the x cubed, so that's the square root of 800 cubed. If I crunch this, I actually cheated, folks. I crunched this in a calculator, but you could do this by hand, not too difficultly. You get 8,000 square root of 2. But let's go ahead and give a decimal approximation of that. That's approximately 11,313.7 centimeters cubed is the max volume that we could make. So for an open top box, let's return to the beginning. For an open top box that has this as its constraint, we must use 2,400 square centimeters of material. We find that the maximum volume that we could make is a box that holds 11,313.7 centimeters cubed, and that happens when the base of the box measures 28.3 centimeters. Okay, so let's go ahead and look at question number 17, and if you haven't read through it yet, you really should pause the video and read through it and ask yourself how it's different from the last question. So in the last question, let's flip back to it for just a second. In the last question, we came up with both an objective and a constraint, and our objective function, the optimizing function, was a volume function. In our constraint, we were constrained by the fact that we only had 2,400 centimeters cubed of material. If we look at this question, it's the same scenario. We have a square box with an open top, but instead of saying how much material we have, we're told that the box must hold 6,400 centimeters cubed, so it's a different sort of constraint. And then we're asked to find the dimensions that will minimize the amount of material used. So in this case, our objective function, or our optimizing function, or our max-min function, is going to be m of x h, which is, we said last time, was 4x h plus x squared. If you have any questions about how I got that, go look at the scenario from the previous video. Okay, so we're asked to minimize the amount of material used, and we're subject to the constraint that the volume must equal 64,000 centimeters cubed. Okay? Well, the volume is, in fact, let's go ahead and write it as a function, or write it in function notation. We have that the volume of xh is equal to x squared times h. Remember, that's length times width, because those are the same, times the height. So all of this applies to this open top box. Here's x, here's h. Okay. So I can make that solid. Okay. So ask yourself, how is this different? In the previous question, our objective function was we wanted to maximize volume. Now we're trying to minimize material used in constructing this box. Okay? And in the last problem, we were constrained by the fact that we had only 2,400 square centimeters of material to build the box with. Here we can use as much material or as little material as we like, but it must hold 64,000 centimeters cubed. Okay, so you can see that this is sort of the reverse of this last problem. Okay, so in this case, we're going to solve the constraint. So we've got 64,000 equals x squared h. Let's solve this constraint for one of the two variables. Well, again, I have a choice. I don't have to solve for either of the two variables. I could either solve for x or I could solve for h, but I think it makes sense to solve for h, because if I solve for x, I'd introduce a square root into this problem, making it more complicated than I need to. So we see that the h, the height of this box, could be given by 64,000 over the square of the base. Okay. So now that I've got the constraint solved for a variable, I'm going to plug this into, or substitute into, the objective function. Okay. So if I do so, we get that the volume now is just a function of, not volume, that's not our optimization function. It's m the amount of material we use, is now just going to be a function of x that's equal to 4x, and in place of h, I'm going to replace the h. Let's see, where is that h? Here is the h up here. I'm going to replace this h with the expression that we found h to be equivalent to. Okay, so that gives us the 4xh plus then the square of the base. Okay. So now we've got the objective function written as a function of just one variable. Before I start taking the derivative, we've learned that it's easier to clean up a function first. And so if we do so, oh boy. So we get 256,000 over x plus x squared. Okay, so now we've got this materials function, the function that we're trying to optimize. We've written it in its simplest form. So now we can go ahead and optimize it. So how do we do that? Well, we're going to look for the critical numbers first. And this would give us negative 256,000 over x squared plus 2x is the derivative of this function. So if I did that too quickly, just pause the video and take the derivative as you normally would. See, this is what you get. So notice that this function is undefined if x is 0, but we're not going to count 0 as a critical number because the original function wasn't defined there either. So the only other place we could have for a critical number is where this function equals 0. So let's set it equal to 0. Okay, so now there's lots of ways I could go about tackling this problem. I could get a common denominator, or I could add this over the other side. I'd like to go ahead and multiply both sides of this equation by x squared. So if I do so, I get negative 256,000 plus 2x cubed is equal to 0. What did I do here? I multiplied both sides by x squared. Of course, there's many ways to solve this equation for x. This is just the way I chose to do so. So we get 2x cubed then is equal to 256,000, or x cubed is equal to 128,000, or that x is equal to the cube root of 128,000. You could do the work, it's not necessary, you could do the work to simplify this radical and show that it comes out to be 40 times the cube root of 2. But let's go ahead and give the decimal approximation of this. This is approximately 50.4. So for building this box, and it must have a volume of 64,000 cubic centimeters, then the best way to do so, the most efficient way to do so that will minimize the material, is if we let this base here be about 50.4 centimeters. This would be 50.4 centimeters, and then to find the height, we'll have to do a little bit more work. But before we do that, I'm assuming that we've got the right answer, and we should actually check this. So we're assuming that this is a local minimum, but let's actually check. So if we look at m double prime of x, so I'm taking the second derivative here so I can perform the second derivative test. If I take the second derivative of this, I get positive 512,000 over x cubed plus 2. And I'm not actually going to plug this in. If I looked at m double prime of 40 cube root of 2, well, just keep in mind that's about 50. But regardless, I'm plugging a number into this function. What's the sign going to be? Well, this is a positive number. I'll cube it. That's positive. I'll divide it into a positive number. So that's positive. So this whole result is positive. And then I'll add a positive number to it. This is always positive. So what do we know? We know that this function at x equals 40 cube root of 2, keep in mind that's just about 50.4, the function is concave up because the second derivative is positive there. So where on this interval could we be? Well, we also said that this value is where the first derivative is 0, so we've also got a horizontal tangent line. So where on a concave up interval do I have a horizontal tangent line? The only place that happens is at the local minimum. So by the second derivative test, x equals 40 cube root of 2 is a local minimum. Okay. But this was the only local extrema when we found where the first derivative is 0. It was the only solution to that equation on the for all real numbers except for 0. But anyway, it was also the only one on the interval from 0 to infinity, so we could say that it is also a global minimum. So that's by the 4.5 theorem. It's also a global min. As a reminder, that formula was, or that theorem was the one that said if you have just one local extrema on an interval, then it is also its equivalent global extrema on that interval. It's a handy formula that's preventing us from having to check the endpoints for finding the global extremum. Okay. So we do know that we've got the global minimum when x is this value here. Now we just need to figure out what h is, because we were asked to find the dimensions. Well, if we go back to where we solved the constraint, this is a typical trick, folks. So way back at some point, we took our constraint and we solved for the variable h, and that we eliminated h from our function. But if we want to actually find h, we can just go back to this equation right here where we solved the constraint for the variable h, and we'll just input in what x is. So going back to that, we said then h is equal to 64,000 divided by 4x squared, but here we're saying that x is 40 cube root of 2 squared. Okay. And this is a perfectly fine place to park your answer. I'll go ahead and get a decimal approximation of it. So when I plug this into the calculator, I get approximately 6.3. Okay. So it turns out that the let me pause this real quick. Hey folks, my apologies, I need to double check this. When we solved the constraint for h in the process of copying down, I added a 4 there that wasn't there, so I need to go back and erase this from here. I'm not going to clean up the video, we'll just leave it at that. So that's going to change my decimal approximation to 25.2. 25.2 centimeters. Sorry about that, folks. That's just how it goes sometimes. Anyway, so we found that the dimensions that will minimize the amount of material used are 40 cube root of 2 by 40 cube root of 2 by, and then 64,000 over 40 cube root of 2 squared. And you could leave the answer this way. I think it makes more sense to give a decimal approximation in this case, and that decimal approximation was 50.4 centimeters by 50.4 centimeters by 25.2 centimeters. And you can check this indeed has the requisite volume of 64,000 cubic centimeters. So I think that each of these problems is interesting in their own right, but I think that a good skill to develop as you're learning how to do these optimization problems is to compare and contrast these two problems, see how they were similar. They both had to deal with open top boxes with square bases, but how they were different. One was a maximization problem where we were trying to maximize the volume, and one was a minimization problem where we were trying to minimize the amount of material that we used. Anyway, I hope this was helpful, and let me know if you have questions.